actually checked my recording this time to make sure it records audio, so I'm already starting off better than we did last time. Okay. So, question 1. We use a processor with the CPIs for the following classes of instructions to execute the given C code. For array B, then 40% of the instructions are not zeros for the if-else statement, assuming that the branch instructions assuming that 2 branch instructions are executed if the branch condition is true, the then path is one branch instruction if the execution branch is false for the else path. Every array reference needs a load store instruction. Answer the table. 1. The number of instructions executed for each class. 2. The number of cycles executing each class's instructions. 3. The percentage of cycles with each class with respect to the total cycles. Also answer the questions after table. Overall total number of instructions, total number of cycles, and the average CPI. Addition used for calculation. Okay, so okay. So one of the most important things about this question right here is this line. How do I highlight them? Highlight color. 40% of the elements are not zero, and so that indicates with this. So, and it says for the if-else statement, assuming 2 branch instructions are executed if the branch condition is true, the then path and one is true, and then the else path is one branch, its execution is false. So you're going to get 2 branches 40% of the time, 1 branch 60% of the time. So keeping that in mind, this for loop, the way we've taught this class, you got 2 branch statements for the for loop. Now we'll go into this else statement. So we have 2 times, what is that, 24, and then plus 1 times 0.6. And then, so 1 times 0.6 is 0.6, and then 2 times 0.4 would be 0.8. So overall, this should equal, wait, this is add, my bad. Control X. Overall, this should be 3.4. Okay. So now I will go up here to this add statement. Oh, it's for adds. So once again, like I said, you have an add statement here for the for loop. So you have that one. And then it's kind of the same deal with, you have, let me choose a color to highlight. Let's make these green. So you have an add statement there, an add statement there, and an add statement there. So you have 3 adds times 0.4 time, 40% of the time, and then you have another add here and another add here. So 2 adds 60% of the time. So point. Let me get my calculator. Oh, I already passed this class, so I can use a calculator. 3 times 0.4 is 1.2 plus 2 times 0.6 is 2.4. Okay, so once again, 3.4. And then load store. Okay, so we'll highlight those in a different color. So this is going to be a store. Oh, that is text color. My fault. So that's going to be a store because there's that equal sign. But we also have it's a plus equals, so that's the same as loading it in and then storing it back into that address. So we have a load and a store. So you already have 2. And then another load right here. And another load right here. So that makes 4. Oh, my fault. This load right here, almost forgot. Even though, so what I'm assuming with this problem is he loads everything in. Well, even though you load it to do this if statement, we load everything again in this one statement. So times 0.4, and then down here, another load. Oh, another store. Another load. Another load. So that is. Wait, I'm putting this on the wrong thing again. Plus 3 times 0.6. So 4 times 0.4 would just be 1. So this would be 1, so that's 2. And then 3 times 0.6.
4 times 0.4 is not 1.
Thank you.
1.6.
I was going to say this math isn't mathing. I didn't pull out my calculator for that one, see? This is how we all make mistakes. This is 1.8. And then, so 1.6 plus 1.8, it's another 3.4. So that will be 4.4 for this one. Okay, so does everybody understand kind of how I got to these numbers for each instruction type? Okay. I'll take that silence as a yes. But next part, cycles, easy math. 0.8 and then 10.2. Cycle percentage. So let me just go ahead and do this. So you have 3.4 times plus 4.4 plus another 3.4, which equals 11.2 times 10, because we're doing 1,000 instructions, so 10 to the third. And then right here, you're just going to add everything up, so that's going to be your 6.8 plus 52.8 plus 10.2, which is 69.8 times 10 to the third. So now what we're going to do here, since we already put those down, we're going to, our cycles, which you can leave them like this, so 6.8 over 69.8, and then for this one, 52.8 over 69.8, and then for this one, 10.2 over 69.8. You can leave them like that, so you don't have to worry about doing arithmetic wrong or like dividing. So that is a acceptable solution. Now, average CPI is just total cycles over total instructions. So that's going to be your 69.8 over 11.2. I'm ignoring the 10 over 3 here because they're both to the same power, so it doesn't really matter. And so that gives us a 6.2 average CPI. Okay, so that is that question. Anybody have any questions? Okay. Oh. Okay, guess not. Is there a draw on Google Docs? Oh, there's not.
Yeah.
If you go into insert, there's a drawing thing. I don't know what it does, but
Oh,
I think that works.
wait. Can I? Okay, hold up. Let me close. Copy. Insert. Drawing. No. Copy. What? Okay. I don't know.
I think if you want, I can probably share my screen and I can like draw. I
Yeah,
can like
I'll
draw.
let you. Yeah, you can share your screen. Everybody migrate to Christian's cam whenever he puts it up. And then you can just paste it into your picture into the document over this one.
All right, let me see what we got. Okay.
Are you sharing?
No, not yet. Let me see. I'm copying and
Okay.
pasting like the image and stuff and see if I can. Can I do? Oh, maybe let me just do this here. And then,
you might be able to copy paste it into Paint and do it that way.
You can also do that with the snip tool. You can
Yeah,
snip it.
that's what I'm doing right now. There we go. Okay. So let me go ahead and share my screen here, and okay. So I don't have like the actual problem, but like I guess let me see if I can copy that in. So basically, we're given number 2. We're given like.
Whoa.
Well, okay. So there we go.
Yours is
So we're
still
given.
loading for me. Is anybody else having this issue?
Yeah, it's still
It's
loading.
still loading.
Who's
Okay.
it?
Yeah, it's
Well,
just a bunch of squares.
Oh, you don't see like my screen right now, or
No, we cannot see your screen right now. Still loading.
oh jeez.
I can do this. I can put this on MS Paint and then do this one and then Okay, let me.
This one was always gonna be a tricky one, but
Yeah, I don't like this. Well, the problem's not bad. Doing this
yeah,
problem.
yeah, it's just drawing out on it.
Snip.
Um,
Okay. Open with paint. Let's go. Okay. So the instruction. This is recording this, right? Okay, cool. So the following diagram shows the data path and control signals for a 5-stage CPU design for load store and ALU operations. We will introduce LI instruction, which is in the format of LI, register destination, and immediate. This instruction performs the following. Well, performs loading an immediate number INM to register RD. If you implement the instruction using provided CPU diagram, the data path. So they want you to kind of go with the. Let me insert some text here. So we want an LI, RD, then IM, and then, even though it doesn't say it, we're going to treat that as a register. Oh, that did not. Okay, wait. You guys get the idea. So, do you want us to highlight certain things, or is it fine if I just do all? To draw this word, use highlight the data path used for the LI instruction. Okay. Colors, yellow. Brushes. We want just this brush is fine. Okay. So we have a register destination. So we're going. This is our register destination right here. This is read register 1 because we have a we have to have a register and the immediate. Then we have an immediate that goes through here. So this retrieves the value from the register x0 and goes and puts it in read data 1. This mutex right here, or mux, is being used to tell the ALU to take input from this wire and not read data 2. So now I'll change the color. We'll do red. So the result, okay, so he wants you to specify what ALU operation we're doing here. We're doing add because we're adding to get address. That does not look good. I'll type that in later. So make sure that you say what ALU operation you're using when you come to the test. And if you've done the homework, you know that like on that little chart, it tells you what type of operation it does in the ALU. And the load word does add because you can remember. Okay, so we're not going to bother going through this memory block right here. We're going to go around it because this is purely, well, this part right here is for writing back into the system memory. So we're not doing that right now. We are getting a value from a register and then putting it, well, getting a value from putting it into a register. So we go around here and then we take this all the way around and then up and then through here. And now you're done. That's all you have to do. So My drawing sucks. Add. Okay. Oh, also remember to don't do what I did and highlight your little flags. So. Okay. That's it for this one.
And Michael, do you remember which one you got on your test?
I got this one. Wait. I got something actually, yeah. I think I got this one. I think I got a load word instruction.
Okay.
Yeah.
Yeah. I would recommend looking at all of them because the add one's pretty simple, but the load, store word, the branches, they're all different from each other. Because when I took this class, the one on my test, Dr. Yan created an instruction for us to figure out the data path for. So we actually had to know what like if it had RS1, it would go through read data one. If it had an immediate, it would go through the immediate generator. And if it goes to the ALU or not, if it reads from memory or not, or writes to memory. So make sure you look at all the other data paths too, even though in this example it's just add or load.
Wait. Wait. Insert. There we go. Okay. That's on there.
Yeah.
So, okay. Now we'll get to go to this fun question. I'll let somebody else take the wheel.
Yeah. Do you want me to, Zach? Do you want to do this one, or do you want me to do?
I'll take it.
Okay. I mean, all right.
All right.
Go.
So for question 3, where's the instruction? But given the following CPU diagram, and it's gonna be the same thing you use for homework 4. And just fill in the table with the values for the selected data path for each instruction when being executed on a CPU. So we have 6 registers and 6 values in each. No, that's 7 registers. Okay, 7 registers and 7 values in each register, and we have 6 memory addresses and 6 values in those memory addresses. So given these instructions, we're going to want to look at what's in the registers, perform the operations, and what data paths in the CPU will take. So we're going to start, I guess we'll look at the first one. So the first one's add x3, x2, x1. You should know that the default or the general syntax for these instructions is register destination, register 1, and register 2. So first we have register 1, that's going to be x2. Then register 2 is register x1. Register destination is register x3. And so RS1 value, or the ALUN1, so we're going to look at RS1, which is 2, and we're going to go up to register number, find 2, and it is 12, so we put 12 in RS value 1. Same thing for RS2. We look for RS2, which is 1, go up to the register number, look for 1. In register number 1 is the value 8, so we put 8 there. And because this is an add, the value in RS2 is going to be going into the ALU, so we just put the 8 in ALU into as well. And so what comes out of the ALU is RS1 plus RS2, which is 12 plus 8, which is 20. And then for the next one, it's memory data. So an add instruction does not access memory, doesn't read from memory. So we can just X that out. Don't know what I did, but just X it out. And then write back data, it'll take 20 from the ALU and write it back to X3. So 20 is what we write back to the register. And the next instruction is, our current instruction is at 2. and it's going to be plus 4. So the next instruction is 6. All right, so for a sub instruction, we can just do the same thing. It's RD, RS1, RS2, so 4. I mean, red for some reason. 4, 2, register destination is 6. All right, I guess we're just going to be red. And so what's in RS1 is in what's in 4, 26. This one's going to take a while, isn't it? RS2 value. All right, so RS2 is 2. So what's in 2 is 12. And it's a sub instruction, so RS2 is going to be going to the ALU. So 12. And what comes out of the ALU? It's 26 RS1 minus RS2, so 26 minus 12. 14. It's just a simple sub instruction, doesn't read from memory. We're going to be writing our 14 back, and plus 4 to our instruction count, 12. Or an OR instruction is an R type instruction, so it follows the same thing. RS1 is 2, RS2 is 0, our register destination is 3. And so what's in register 2 for RS1? It's 12. And the X0 is just going to hold 0. And it's an R type instruction, so what's going in the ALU and or ALU into is also going to be what's in RS2, which is 0. And so an OR operation is a bitwise operation. It's going to look at every single bit in both of them. And so because in OR it's going to be 0, 0 and OR 0 is 0, 0 or 1 is 1, 1 or 1 is 1. So all you need to know is that if something or 0 is the something, so what comes out of the ALU of 12 or 0 is just going to be 12. And so we're not reading anything from memory, but we're going to write back our 12 to register 3. And we're at instruction number 12, add 4. The next instruction is 16. Okay. So add I is register destination RS1 and immediate value. So RS1 is going to be 4. There is no RS2, so we can just X that out. And register destination is 2. So RS1 value is what's in 4, and what's in 4 is 26. There is no RS2 value, but what is going to be going into ALN 2 is our immediate, which is 54. And so we're going to be adding our immediate plus RS1, which is 80. We're not reading from memory. And what we're going to be writing back is what comes out of the ALU, which is 80. And our next instruction, we're on instruction 24 now. So add 4, next instruction is 28. Load word. So load word is going to be register destination, comma, offset, and then RS1. So here, RS1 is going to be 2. We have no RS2. And our register destination is going to be X5. So we can put 5. And what's in RS1? What's in 2 is 12 still. There is no RS2 value, but what's going to be going into the ALU is our offset, which is 18. And what comes out of the ALU is what's in RS1, which hopefully is going to be a memory address, plus our offset. So what comes out is 30. And then, so we have a memory address of 30, and load word does read from memory. So we're going to go up to our memory addresses, find 30, and the value in memory address 30 is 32. So we read 32 from memory, and load word also writes back to a register. So we also have 32 to write back to the register. And this is instruction 32. So our next instruction is 32 plus 4, 36. Store word. So store word is a little different from other instructions in its order. So it's going to be RS2, comma, the offset RS1. So in our case, RS1 is going to be 4. RS2 is 6. And store word has no register destination. And so what's in RS1 is the same is what is in register 4, which is 26. And so we get RS2 value is what's in X6, which is 6. But 6 is not what's going to be going into our ALU in 2. What's going to be going into ALU in 2 is our offset, which is 12. And so what we're going to do is going to take what's in the memory address that's in RS1, and we're going to be adding our offset to it. So we get, what is it, 26 plus, which is 38. So 38 is the memory address that we're going to storing into. But for store word, we do not read from memory, or yeah, we don't read from. And we're not writing to a register, so both those are X's. And we're on instruction 36 plus 4. Next instruction is 40. All right, so now we have branches. So a branch is going to be RS1, RS2, and then the label or the offset that we're going to be jumping to. So RS1 is 2, RS2 is 4. We have no register destination. And so for RS1 value, we look at what's in X2, still 12. I'm checking every time though. What's in RS, which is in register 4, still 26, still checking. Okay, so 12 and 26 are what's in our 2 registers. And so what's going to be going into ALU in 2 is what's in registered RS2, which is our X4. All right, and so a branch not equal. To check if the things are not equal, branches are going to use subtraction operations. So it's going to subtract the 2 numbers. So it's going to take RS1 subtracted by RS2. So in our case, 12 subtracted by 26. And we're going to get negative 14. And so if they would be equal, we would get 0. And then it would know not to branch. But we are going to branch this time. But first, we don't read memory, don't write back to memory. But we didn't get 0 when we subtracted our 2 numbers. And we branch if it's not equal. So that means we're branching. So our next instruction is not going to be plus 4, but we're going to take our offset, which is 24, and we're going to multiply that 24 by 2, which is 48, and add it to our current or instruction address, which is 40. So the next instruction is going to be 88 when we branch. So break if equal, same structure, RS1, 5, RS2 is X6. Don't have a register destination. What's in register 5? It's 10. What's in register 6 is 6. What goes in the ALU in 2 is 6, which is our RS2. And then so branch is a subtraction operation. We take RS1, subtract RS2. We get 4. But before I do more with that, we don't read from memory. Go right back to a register. All right, so we get 4. And 4 is not equal to 0. But we branch if they are equal, but because what comes out of the ALU is not 0, that means that they're not equal. So we do not branch. So since we don't branch, the next instruction is once again going to be the current instruction address plus 4. We are on the instruction we're on is at address 60. So the next instruction is going to be at address 64. And that's the table. Yeah. These ones are pretty straightforward. Just look at your registers, look at the values in them. Yeah, I would say the hardest part is you have to, for the branches, you have to know if they branch or not. And you have to calculate the address and then make sure that your next address is going to be your offset times 2 plus whatever the address is of the instruction you're currently at.
It's a long question. I know you guys have a time limit on these, so make sure you look at the percent each question's worth, and then kind of evaluate where you want to go. Because this is 36%. The first one we did was 24, and then this one right here is 10, and then 4 is 10, and then 5 is another 20. So if you don't get your first 2 right, that's 60% of your grade. Well, 1 and 3, like that's 60% of the grade right there. So make sure you prioritize higher value questions first.
Yeah, and you're still allowed your sheets to take into the test, like any notes you have on the paper. So if you wanted to, you're probably going to be given a table just like this on the test. You can just fill out a table, this one if you want to, of just examples of each operation, like an add operation, sub, load word, sort word, and a branch, and then just fill out the table, and then just put that in your notes. So you have something to look at if it helps you. Just to look at what should be going to each one of these columns.
I got a quick question on that one. For the branch not equal, I noticed to get the BCNX you did the offset times 2 plus the current address. But for the branch if equal, you just did offset plus the current address. Could you explain that a little bit more?
Oh, so branch if equal, I guess that's a very unfortunate number that the branch if equal has the offset of 4, because we're not using that at all in this question because x5 and x6, they are not equal, so we are not branching. So we're simply just taking our current instruction address, which is 60, and adding 4, which is the size of a word, 4 bytes, and just adding that onto our instruction address to get to the next address is 64. So
Okay.
we're not even using this 4. But if we were branching, it would be this 4 times 2 plus our instruction address. So we would be going to address 68 for the next instruction if we did branch here.
Gotcha, thank you.
All right. So looks like it's. I'll go ahead and do number 4 here. So I think for this one, it's just like a lot of like what question 3 was just talking about, and just kind of like what Zach was going through, like a bunch of like what like load word and store word and all that does. And so I think, and so to kind of just start going through the questions, I can probably just start on part A. And that's saying like, why is the ALU operation for load store instructions an add instruction? And so just kind of start that off, like this is basically like add instruction because we want to like load the specific address like into the memory. And so in here, and so then we want to um use add in the ALU so that we can perform so that we can calculate like the effective address. That's honestly pretty much it. Like, and then if you kind of want to know like the address of that you can calculate, that's like your RS1 plus your immediate. That's basically it for that one. And that's just kind of like to get like the specific address, like as we were saying before. So for the BEQ instruction, so why is the ALU operation for BEQ instruction a sub operation? That's like that's just kind of like checking to see like if both operations like subtracting like both operations to see if they're both 0. So like if both numbers are like 24, for example, for like RS1, like let's say like RS1 is 24 and RS2 is 24, like has like the values of 24 and 24. And then we want to check if they're equal or not. We can just like do 24 or just do like 24 minus 24 to check whether or not like those two branches or those two like registers have like the same value. So for this one, we need a sub operation for the ALU to check if both RS1 and RS2 when subtracted equal out to 0. And so then if it is 0, then that then those two source operands are like equal. And so then for part C, why is the ALU source control for add is 0, and then like the add load and store is 1. And so for that one, that's just because like for like whenever you have like the add the load, and a store, that has like your immediate value. Whereas with the add that just has like that doesn't have like your add like or your immediate value at all. So and with the ALU source control, that kind of chooses between like whether or not you want to use an RS2 value or like the immediate value. So the ALU source is used for when we want to select like either RS2 or immediate to use for like the ALU output or input, I mean. And then this means that like 0 is used for the RS2, and then 1 is used for the for selecting the immediate value. But does anybody have like any questions from here? Just kind of like before I kind of move on to E&E. All right. Go ahead and take that. There's no questions. So, so for part D, that is the memread 1 for load, but 0 for store. So for the load, one way I kind of like to think about it is like when you're loading like when you're doing like the load word instruction, that's like loading like pretty much like let's say you want to load up like x6 like x5 of like this array. You want to load up like the contents of like we kind of want to read like the register bit so that you can use that like within your like within like the add operations and kind of like whatever like you can within the x5 to kind of read the contents of that for store because for that that's like because for store that's just like storing that back into like the memory and for like the store word whenever you're like storing like the array back into the register, you're not gonna like read that at all. You're just like storing that in and you're pretty much done. So for memory, X is used for the load instruction. So that we to read the memory. So the difference. So then we say that store, like store word or store instruction does like uses memory, right? Which means that we should put the memory to zeros as it doesn't use that. Okay. So now for part D, Y is the reg write control, 1 for add or load, and 0 for store and BEQ. So for that, that's just I think that one that's just like because like all of the add or and load, it all has like your RD. And then for the store and BEQ, like for the store, it stops like at the data memory, because you're kind of storing the contents of like whatever register you're trying to store in, and then it stops from there. And then for the BEQ, that kind of checks for like your PC or PC plus 4, but or that kind of checks for the condition as like Zach was doing in the previous problem, and like if like a condition holds true, then it does like that PC plus label times 2. And so that kind of goes through that goes through all that operation, and it doesn't like really touch like that reg write fit. And so we can say that reg write means that register write should be used for the instruction. Add I or and load all kind of I'll write like the results of like results of their instruction or write the results back to the register. Probably write it like that. And then so that means that they need that means that they need the reg write control. In other words, we'll need to store. We'll need to write 1 for or set reg write 1. Okay. All right. I think that should be everything for me. Does anybody have any questions? By chance?
Oh. Okay.
All right. I think. Go. Yeah.
Yes.
I'll go ahead and like. Go ahead and like change the colors. The color for it to kind of differentiate the answers, I guess.
Okay, so 5. This is like question 3 on your homework. Pipeline execution and raw read after write data hazards for the following RISC-V cycle instruction sequence. Is that the Wait. Is this the answer? Yeah. Okay. Fill in the following raw dependencies between two consecutive instructions and also mark ones that are load use. Okay. So the first one they give us, they use this add I has x0 plus 4 and then writes it back to x1 and then immediately uses x1 right here. So this right here is a dependency with the register x1. Nice. This one right here is not a dependency. Doesn't have a hazard because there's a cycle of those instructions between it. Same with this one here. It is not a hazard on any of the ones above it. So now we'll look at this one right here. Load add 5, x4, x10 stored into x5. If you notice, x4 right here is being loaded from, well, is being written into in this load word, so it is being used here. So let me highlight this, Control C, Control V, and then Control C, Control V. The register in question here is x4, and we will highlight this as a load used. The reason this is a load used is because you're quite simply loading into x4 and then using it right away. So next, x5 is being written back into here and being used right there. So Control C, go do that. I don't need to tell you that. Control C. And then the register in question here is x5. This right here is writing into x6. x6 is being added in, well, used in this add statement right here. So register in question. And then Control C, Control V, and then x6. And then finally, this add right here is writing into x7, and then we're storing x7 into memory address 0 plus x1. So there's a register. The register in question is x7 that leads to the hazard. So pretty straightforward for that one. Since that one was short, I'll go ahead and do B. So B is draw the 5-stage pipeline execution using the labels IF, ID, EX, ME, and WB. CPU has no forwarding. Register files can be read/written to in the same cycle, and instruction memory and data memory are separated. Use X to indicate the stalled cycle. So this table does not fit on the page. Is there a way I can make, because there's not going to be enough lines here. Can I shrink it? Just edits, add comments, paste. Okay.
I think other than like other than part B, I think we should be like good. But on like how many cycles we can have. Because yeah.
Ah.
There it is.
Okay, so using the same, I think this is the same instructions as earlier. So we already marked this right here as a dependency between the first two instructions, so we will mark 2 stages of delays, and then that's going to be annoying. I'll play around with that in a minute, because It's going to be a lot of dragging. Actually, I'll just fix it. They call me an Excel wizard. I just want to make 9 a little bigger. Okay. There's no dependency between the first of these two instructions, so it's going to execute normally. Same with this one. There was no dependency, so it's going to execute normally. Dang, I messed up. There was a dependency with this add statement though, so we will have a 2-cycle delay and then another instructions. Then let me line this up, so that's IF. There was another 2-cycle delay here with the X5. Well, there was a hazard with X5, so we're going to have a 2-cycle delay. Here there's a hazard with X6, so we're going to have another 2-cycle delay. And then with the store word, there was another 2-cycle delay. So okay, so that's that part. Does anybody have any questions for that question? For the first two? Does that fix all of them? No, it did not. It's just tedious. Okay. Zach or Christian, you want to do C or D since it's a...
Like, see, how'd you do the copy and paste thing? Just copy the
Yeah, I just
thing,
copied
just-
the whole row.
and it'll just know to put them in the rows.
Yeah.
Pretty impressive. Okay. So for full forwarding, we no longer have to wait for an instruction to write back to the register to get the value that is going to be written back to the register. We can just take it straight after the execution phase, and we can use it then. So that gets rid of our 2-cycle delays, and so we can just go straight from execution into the execution of the next instruction. So the dependency that existed between add-I and load word, the first one, where add-I writes into X1 and load word reads from X1, that yeah, it does do it. Yeah. So we can just take from the execution phase of the add-I instruction, so we can just go straight into the execution of the load word. And then I don't think there are any dependencies for the next two loads at all. So that's just going to be the same. But so our next dependency is load word. It writes to X4, and the add is reading from X4. And so the thing about load word is that in load word's execution phase, it calculates the address, but it doesn't retrieve the value that's going to be writing back to the register until it reads from memory in the memory phase. So we have to forward from the memory phase. So that means in this case, we're still going to have a 1-cycle delay, so we can get it from the memory. So for this one, it's going to be 1 off. We can just put X here for our 1-cycle delay. And as you can see, once the load word hits the memory phase, we're going to get the value, and then we can just forward it to the execution of the next instruction. And then after that, all the other dependencies are just add instructions. And in that case, we can just forward from the execution phase of those instructions to the next one. So I don't think we have to worry about any other cycle delays.
I don't think you do. I think that one ends at 13, so that's 13, then you're good.
Is it 13?
Yep.
Yep.
All right. So moving on to our second, I guess I'm good to kind of move on to part D, right?
Yep.
So honestly, for part D, it's just like a matter of like, you kind of want to just move like, some instructions around, or at least one instruction around, and get rid of like this, like load use or this load use hazard. And that's kind of saying, okay, we're loading up. We have X4. I'm being kind of like loaded up for the first time, and then it kind of uses like then it's used like right here. And so honestly, like the only thing that you kind of really need to do is just kind of like just switch this bit. Yeah, you can switch this one. Like switch these two like segments around. So it's honestly just gonna be like. Let me see if I can. Hopefully, I can. Yeah, there it is. So you can just switch these two guys around. Oops, and then so that's gonna be something like that, and then switching these guys around so that you can get rid of like that load use hazard, and then from there that's pretty much like you're pretty much good to go, like into getting rid of like that load use, and everything just goes in just like that. Or did I do that right? Or
You don't need the last one.
oh yeah yeah yeah. I was wondering why, because it was kind of like the same amount of cycles, but it should be one less. But otherwise, that's pretty much it.
And that's it for test 3.
Yeah.
Anybody have any questions? Don't forget to write your honor pledge for your exam. Yeah. Anybody have any questions about test 3? You pushed it back till next Thursday, if I remember correctly. So you guys get a little bit extra time. Enjoy your long weekends, and then have your homework due Monday. So.
Can I ask a quick question?
Yeah.
For number 3, when you guys did the B&E instruction, what is when you multiplied 24 by 2, what is that 2 for? Why did you know to multiply by 2?
I'm not. It might say in the slides why you multiply by 2, but and just know whenever you have a branch statement and the value equals true, to get the offset, you have to do the immediate times 2 to get your instruction address for your next instruction. So, like, I would write that down on your paper for your like cheat sheet.
Alright. Thank you, then.
No problem.
I don't remember where, but or specifically, but it was around Lab 6, whatever those slides were.
Yeah.
It's where it went over that.
Thank you guys. Appreciate it.
No problem.
No problem.
Could you just scroll down all the way to the bottom? Like I just missed the reschedule part. Yeah, thank you. Yeah.
Let me bold the ones that are rescheduled.
Yeah.
This one's a lot simpler than your homework for the rescheduling. You only need to move 2 lines. Do we have office hours tomorrow because it's Veterans Day?
I just have one question for the full forwarding. Like I understood all the other ones, but after the load, we have like 1 cycle delay. So why is it just like
So
1 cycle delay and not 2?
so the way that I'm pretty sure it has something to do with the way they lay out the CPU circuit, where you can bypass um, half of half of the instruction, like a normal instruction cycle, which is 5 of these steps. So that's
Mhm.
why there's a delay. Oh, I mean that's why you can get down your cycle from a load use from 1 to 2.
Oh, okay.
I mean, so the reason it goes from 2 to 1 instead of like not completely going away like all the other dependencies is because in the other instructions, like in an add instruction, you get the result in the execution stage. Like that's where you add the two numbers. And so you have your result in the execution stage. So you can just take that and pass it down to the next instruction in when it's doing its execution stage. But for a load in its execution stage, it's adding the address that's in RS1 plus the offset. So, but that's not the actual value you want. What you want is in the memory stage, it accesses the memory at that address that you calculated in the execution stage, and then it retrieves the value that you do actually want. So it can't actually pass its value to the next instruction until the memory stage. So as you can see, the memory stage is lined up right before the next instruction's execution stage.
Oh, okay. Okay. Understood. Yeah, thank you.
Okay, I think I might go ahead and end the recording.